Good day everyone, I'm Sanketh. And me along with Gokul here will be presenting on lossless convexification for the planetary soft landing problem. We have used three reference papers and we will explain few concepts here regarding the linear algebra. So what is a planetary soft landing problem? Now the aim of the paper is to achieve the soft landing in any planetary mission. So it has multiple phases. Firstly, a steep descent phase, a gradual descent phase, and then a powered descent phase. And now in the powered descent phase, a few boosters are switched on. That means thrusters are switched on, wherein you optimally land at a desired point. That is the aim of the paper here. Now the dynamics are modeled, the nonlinear dynamics of this descent, forward descent phase is nonlinear, and the state and control constraints are non-convex. So the cost functions formulated are also non-convex. So it has to be convexified, and then optimization algorithms are performed on it. So there are two main problems which are addressed in this paper, which is a minimum landing error problem and minimum fuel usage problem. So why convexification? So if there is any non-convex problem, the optimization of non-convex problem is generally non-optimal solution, and then the convergence also is not does not happen in a finite time. So that is not desired. So we convexify. That means we transform whatever the convex functions, non-convex functions, to a convex function, and then apply the optimization algorithm so that the optimal solution is achieved, and it is achieved in a finite time. So basically convexification is conversion to convex problems. Non-convex problems to convex problems is convexification. So in the problem here, firstly we'll introduce what exactly the problems are, and then few concepts involved in the linear algebra. So here we are addressing it as problem 1 and problem 2 here. Problem 1 involves any state dynamics. It's a generic state dynamics which I have shown here with control input and some constraints on the control input as well. So if such a constraints are there, and these constraints are non-convex, then the problem is to convexify. That means transform this entire problem to a problem 2, wherein the problem 2 is convex, by introducing a slack variable. Now this slack variable also appears in the cost function such that the entire problem is convexified. Now the process of this convexification involves various proofs, wherein we will use Hamiltonian function for the for optimization, etc. So we will try to explain how are these proofs of convexification using linear algebra is explained in this paper. So let's go step by step. There are few concepts of controllability and observability which is involved in the paper. So we are introducing that in this slide, wherein if the system dynamics is modeled like this, which is a linear x dot is equal to ax plus bu, then a solution to this is straight away can be obtained as an exponential for a given x naught. So that means given initial condition for a given u. So this e power at can be expanded further as shown below. So the x naught, the state x naught, is a function of a matrix formed by this, which can be for a given control input u. So a system is said to be controllable if and only if this matrix has full rank. That means it has all the columns linearly independent. Then the system is said to be fully state controllable. This is the concept of controllability. Next comes to the observability part. Given an x dot is equal to x and y is equal to cx, that means x dot is equal to x is a system dynamics and y is equal to cx is a measurement dynamics. Now if given these two points, we can again formulate this as a y of t is some matrix into x naught. That means we are reconstructing this x0 given the measurement. This can be fully reconstructed only if this matrix is invertible. That means this matrix should have all the columns linearly independent. That means it should possess the rank of the matrix formed by this should be full rank, which is equal to the number of states. This is one of the concepts used in this paper. So let's go further. Now, linear algebra concept used in convexification. I would like to address that here. So let's say any system is modeled in this way, wherein x1 is a function of some input variable, x2 is not a function of a input variable. That system can always be transformed into a co-state dynamics for a given Hamiltonian. This is a nonlinear system, and that which we want to optimize. So we have defined a Hamiltonian with a Lagrange multipliers. So this lambda naught and lambda transpose are Lagrange multipliers. So we maximize this Hamiltonian and get the optimal solution. Now the process here is we establish a co-state dynamics which are represented by this. Now this co-state dynamics is linear in nature. X dot is equal to ax. Now given y is equal to cx. So if this is observable, that means y of t not equal to 0. If there is any y which is not equal to 0, you can always estimate lambda naught and lambda. So that means the system has to be observable. Now this system has to be observable in the sense you have to have this pair del x f and del u f, which is the Jacobian of f and the Jacobian formed with respect to u for the f. So these two, the pair should be observable. Now this pair, using this pair matrix, we can always form a observability matrix as explained in the previous slide. So this is the observability matrix form. This observability matrix has to be full rank. Now this, after expansion of this observability matrix, you can see the observability matrix as like this. So when this matrix can be fully full rank, when this del u f1 has all the columns linearly independent. That means the nullity, the null space of del u f1 is trivial. That is, it should be 0 only. Then that means this has a linearly independent column. Similarly, the del x1 of f2 should also have full linearly independent columns. That's how the nullity will be 0. So these are the two primary conditions. If these two primary conditions are met, you can estimate a lambda. Once you estimate the lambda, use the lambda in h and maximize the h to get the u. So this is the entire process at each and every step. So this pointwise maximum principle says that we maximize the h at each and every point to get u and gamma, such that this obtained u and gamma is the solution for the original problem 1 itself. So this is the case 1, and I will pass on to my colleague. He will explain the case 2 and the further details.
Okay, hi, I'm Gokul. Let me move on to the next slide. So basically, whatever is being involved in the previous slide is where you have control input. I mean, you formulate the function as with function with control input and function without control input. But here the case 2 involves where you have a function with a constraint with the control input. So for this, what we have to do is you formulate the co-state dynamics as mentioned here. Like you take a term alpha that is dependent on, that is being transformed using the matrix T from the co-state dynamics lambda that is being used before. So this is the process of diagonalization used here, and T is the eigenvector matrix of this Jacobian function f with respect to x. So with this co-state dynamics, what you can do is you can just use you can form an observability matrix as given below. So to have this observability matrix, to have the observability matrix as full rank, you have to make sure that the del u f3 and del x f3 as fully linearly independent has fully linearly independent vectors. So only if that is guaranteed, the whole observability matrix is guaranteed. So this So the next is hence the cost functions of the non-convex function and the relaxed problems of the non-convex control constraint is satisfied be used. This actually is this means okay, so the term lossless convexification, the term lossless here means that the optimal solution for the problem 2 is also the optimal solution to the problem. That is being guaranteed as like the observability condition, the process of convexification might be observable at sometimes or might not be observable at sometimes. So the point of guarantee is when the nullity is trivial. That is only when the nullity is trivial you get an optimal solution for the problem 2, and straight away you get the optimal solution for the problem 1 as well. So the process is like in the problem 1, like in the case 1, you estimate the alpha and you straight away estimate the lambda, and you substitute in the Hamiltonian to get you maximize the Hamiltonian using the lambda substitute, and you get the state and post-state vectors. Moving on to next slide. Now comes the application part, right? Till now we have been explaining the theory of lossless convexification. Now comes the application. The application here is straight away the control input is taken here as the thrust contains, as we are considering the power design. The thrust content has a convex upper bound, or say ρ2, and the non-convex lower bound. The non-convexity comes only under the lower bound condition, and it also has non-convex condition on the thrust direction. So we substitute, this is the state modeling, and coming to the next slide. So this is how we solve for the non-convex. I mean, we convert the non-convex problem to the convex problem. We take a slack variable that is gamma, and we substitute here as mentioned. So the problem here, there are two problems that are being solved. One is the minimum landing error for the power descent, and the power descent with the minimal fuel problem. Next slide is okay. So next slide comes. So the application is over. Now now we move on to the implementation. So implementation is something like, now we have made the non-convex problem to a convex problem. So the convex problem can be solved using many ways. One of the solutions the paper uses is the second order cone program. So the second order cone program, they use, like, the control inputs are being represented using the finite set basis functions. The basis function used here is the Chebyshev polynomial, which is again orthogonal polynomials that are used here. So so these are the results. The next figure here just shows the result of the implementation here, implemented by the authors. As from they start at some random position and end at like arrive at some to the specified position. That's it for the whole paper. And now we summarize the concepts. So this is the flow of the algorithm. What is being done? What is to be done for formulating from a non-convex to a convex? So you formulate the system dynamics corresponding to the state and control constraints. You then using that cost function, you formulate the Hamiltonian with Lagrangian multipliers, and you form the co-state dynamics with change of variables in the state dynamics to linearize the non-linear state dynamics. You solve for those co-state dynamics, that is the Lagrangian multipliers, and using the pointwise maximum principle of the Hamiltonian, you solve for the optimal control and optimal control input and the state input. So this is analogous to the minimization convex optimization actually. And that's it for the algorithm aspects. And now the linear algebra concepts. So now we are coming to the linear algebra concept. The linear algebra concept used here are the change of variables to linearize to make a state for the co-state variables, to make the system dynamics for this co-state variables, and they used matrix trivialization using the eigenvectors for the system dynamics. They used linearization of nonlinear dynamics using the Jacobian. So Jacobian is some kind of a linear transformation at a given at a specific point, and linear independence for proving the observability of the state dynamics. That's it for the presentation. Thank you.